Okay, so I wanted to make this video so that I don't have to repeat myself every time. Um, I guess I am going to talk about a lot of things, um, like derivatives and um, non-vector spaces and in manifolds, which I don't understand very well. And none of them I don't understand very well, but still, one is more than the other, I guess. So you could like the general notion is you can skip the parts that you don't understand. Don't do that in lectures. I mean, I don't recommend doing that in lectures, but you always focus on the things you don't understand in a lecture. But for this one is like for whatever you understand right now. I mean, there are a lot of constructions and all that which makes things easier to understand, but the constructions are hard, so you skip the constructions and focus on the properties that we can understand just by understanding. Properties would be enough to understand, not the construction. Like the major idea is how to do derivatives in higher dimensions. So we have a function from Rn to Rm, how to do the derivative, how to do double derivative, how to do nth derivative, what properties does it have, and how do you write it, how do you like write the derivative function quickly without thinking something like notation. How do you just notationally compute the derivative or something? um, what does notation mean if you want to think about it or something, because notation would be enough if you don't want to even think about a lot of stuff. So we will okay, so if I just write the things in terms of notation, so things will look like there will be a function which would be written in terms of components, where q would be some qi's are all basis vectors and all fi's are just functions from Rn to Rm, and these are like I goes from 1 to m. So this is some formal linear combination, where formal just means that you have done the work but you are ignoring them, or you have not done the work and you are just copying them from people who have done the work or something. I'm sorry, this should be a real function. So this is like, you can imagine this is something like a Rn to Rm function from Rn to Rm. So it has inputs, n inputs and m outputs, where qy's are the basis vectors xi cap something. And if I do want to do the derivative, it would be something of the form something like of this form, something like this, but it will also have I components. So something of this form. Let's just say I have to sum this guy over j is equal to 1 to what is j going from again? So I'm doing the partial derivative, so it will have n components, and this f is also some component wise thingy that will work out to be, well, look, this is not really anything, xj exj. There will be a product here, there will be a qi here, and there will be two sums, j from 1 to n and I from 1 to m. And this q can be anything. So if I want to do the derivative once again, I would just imagine the q is this whole thing is now my new q, and I can use the same procedure over again. So this is the, without knowing anything what the symbol means, I'm doing the derivatives. Like the only thing I know is how to do partial derivatives from Rn, from functions from Rn to Rn. But obviously we want to know more and we want to understand what symbols mean. At least I want to tell. Um, and we also want to go to the reverse, like given something of this form, we want to integrate them and get back f. So this would be integrated over some set, and this would be integrated over the, well, the fundamental theorem of calculus and manifolds is based on how things behave, how the derivatives integrated on the boundary of a manifold. No, the derivative is integrated over the manifold, but you have to integrate the function over the boundary of the manifold. And the symbol they use is slightly different, but this symbol is slightly better. But it will not look the same. There's a slightly difference. I am doing tensor product here, and there is exterior product here, exterior derivatives. Um, Now that I think about it, I don't mm, know them very well, obviously, but still, I know some bits which I don't want to repeat one again and again. So would be some sort of um, the goal, follow the prescription before. So D2F would be defined as D of D of something of this form. Okay, but what are those things? So how do you construct something? Where can you do all this and all that? How general is this? So we will go directly to normed vector spaces. Um, so I will just add in, start with this. You will do, we'll go to a normed vector space. This will have properties. This is a vector space, and there is this function which satisfies certain properties. Um, I am not going to the details of what those properties are, but let's just say that given this norm, norm is just what a usual norm means. Norm will just take a vector v and it will give out some real number, and to be remember for all of this, I will assume it's all reals, real vector space, and this will give you a real number, always a positive real number, and including 0 is greater than equal to 0. I'm not defining the properties, I'm just stating them, I guess, but I think these are the definition properties. Is this equal to alpha norm times x, and it also satisfies a triangle inequality of some sort, and yeah, a triangle inequality such that t of xy, which this is the vector space v, and this is some x, this is some y. So this is x minus y. So I'll just take the distance between the two as the norm of this. This is the standard distance such that v and d becomes a metric space. And this structure, vector space and metric space, vector space with a norm makes it a metric space, and you have plus and scalar multiplication, so you can do addition and subtraction, is enough to do partial derivatives and total derivatives and integration and everything. So you don't need much more. So let's say you want to do physics and you want to put a structure on um, the space-time, a Newtonian space-time. You want to define something like you are working in inertial frames and you want to do that. So this is enough. You don't need much more than a uh, metric and addition. So the norm vector space, that norm vector space would be enough as a structure to do all the work. You don't need a dot product. Dot product is more than this. Sometimes you can convert from norm to a dot product. Sometimes a norm can come from a dot product, but norm are general. There can be some norms which cannot come from a dot product. Dot product is the actual terminology is inner product, which is product between two vectors and which gives you a real number. So we will work in this space. We will try to do derivatives, define derivatives for functions of this form. where this is an open set. I will not define what an open set is. If you have given a metric space, you can define what an open set is. These are all cascading. I like the word cascading. So given a norm vector space, it is also a metric space. So every properties of a metric space will come cascading from that. I think that I was inspired the terminology from CSS, I guess. Yeah, so I will take such a function which goes from, these are both two different non-metric spaces, and I want to define derivative for f and double derivative for f and all that. So if I define it for this one, I have already defined it for any non-vector space, and if this is a funny thing that I will encounter later. If you define something for a general set, you can repeat it, you can construct something and all that, and this is used in manifolds theory also. I mean, that's a very nice thing about abstract, I guess, generalizations. Why generalize? Okay, but to do all that, we have to work with some prerequisites, which I also will explain. The idea is we have to do tensor algebra of a vector space, symmetric algebra, which comes out of the tensor algebra, and the alternating algebra, algebra of alternating uh, elements, and which is also known as exterior algebra of a vector space. So which I wanna do. It's not absolutely required, but these help to to for the understanding. So let's say I have a vector space and I have another vector space. Both are over reals. I'm not going to assume anything else. These are all general ideas. You can define tensor product of two modules also. I've only heard of, not even read. So the thing we want to do is this. We want to convert uh, a multilinear map from V cross W mm, to anything else. Let's say it's V1. V1 cross V2 W, and this is a multilinear map. So this slot, this V1, this slot is linear. So if I put A plus lambda B, it will split into phi of A plus phi of lambda B. Something of this form. Phi of A plus whatever I put in the blank, it doesn't really matter. Plus lambda of phi of B. So it's also linear in the second slot. That's uh, so it is like linear twice. Uh, Made up symbol for linear twice. It's called a bilinear map. So I want to understand bilinear maps, and I know about linear maps only. I know about V linear maps from V to W. So how do I understand them inside linear algebra? Do we have to construct a multilinear algebra now? Do we have to do another semester course? The answer is no. And that would be a very nice thing to say, um, but we can construct another vector space which would look like this, which is one vector space. This is one single vector space, and we can convert this phi to a phi tilde, which now becomes this bilinear map is now converted to a linear map, and my bilinear algebra, now this is monolinear, but okay, linear map. So I've converted a bilinear map to a linear map. I can convert an n linear map to a linear map, um, a- and I can use them. So I don't have to construct a new theory of bilinear maps. Uh, and this is what a tensor product does. A tensor product will create a new vector space such that it has this universal property with other vector spaces. Now, how do you understand this uh, vector space V1 tensor product? This is tensor product V1, tensor product V2. You understand it in this way that if I put the original function, if I put V1, V2 here, they are both linear. And the typical element of this guy would look something like V1 plus V1 tensor product V2. Matlab, I'm saying it has to. Like, so it will contain something of this form, right? So phi will take some element which looks like this, phi tilde, um, and it will map to the same number because they are the same functions. Uh, some element of total. So, so that is what the definition of the universal property of a tensor product is saying. Every multilinear map would be converted to a linear map uniquely. I have used a very horrible notation because phi is something else over there, but anyways, let's just call it f will be converted to some f tilde, so that this happens. Then f of v1 v1 plus lambda v2 uh, lambda u1 comma v2 would be mapped onto something v1 v2 plus lambda would come out simply as v1 v2. So the tensor products of these guys would be looking like this. This the same thing. I mean, it should look like the right hand side and the upper one. So it should look something like v1 tensor product v2 plus lambda u1 tensor product u2. So there is a so this universal property is giving me the picture of a vector space, v1 tensor product v2, whose elements look something like this, and where this operation is not commutative, of course, but associative and distributive over addition and scalar multiplication. So something like v1 plus v2 plus v1 plus v2 tensor product v3, I can contain them in something like this, and this would be a valid equation. So this distributes over the addition and similarly with the scalar multiplication. So now, and this is not a algebraic operation or something. I can't take any two vectors and then do the operation. It's like just the elements of this guy will act in this way using the symbol. So let's say I have a basis for V1 which goes from Fi, and basis for V2 which goes like GIs. Then a basis for V1 tensor product V2 would have to be um, Fi tensor product Gj sum for all ij. So F1 tensor product G1 G2 is not same as G2 tensor product Fj, because tensor products don't, like, there is, because element, typical element would look something like V1 tensor product V2. So this will be coming from V1 and this will be coming from V2. They would not commute, of course, because they can't. Even if I am just doing a tensor product of V1 and V1, they would not commute. So this operation is not commutative. A very horrible way to explain the tensor products, but still, you can understand that if I write random uh, elements of this form, I can't always write it in terms of some pure pure tensors, which are always like this. So this will come from V1, this will come from V2. I can't always do this. This is not always true. So the left hand side would be not a pure tensor, impure tensor. So not, so the but you can always write it as a sum of the basis vectors which contain of this form. So and there are, if the dimension of v1 is n and the dimension of v2 is m, there will be n times m basis vectors in the v1 cross v2 uh, vector space. So that's why the dimension of v1 v2 would just multiply, and that is what we mostly want. If I want a tensor which would take this form, that I have a box and I'm putting the force on the x face, and I can put the force in 3 directions. So I have 9 components. So I will take the vector space, I will take vector space of this form. So it will take 2 vectors, and this would be isomorphic to R9 in the vector space definition, and maybe not in a proper way, but uh, huh, dimensions will multiply. What am I doing? Dimensions will multiply. This is actually this is okay. Um, so this is where, I mean, this has nothing to do with actual tensors, but this is called a tensor product because I think the name came from here. I'm not sure. So we can define tensor product of two vector spaces, which creates a new vector space with dimensions that multiply if they are finite dimensional. I'm working with everything is finite dimensional here. I'm not working with infinite dimension at all. Now, if I have this, then I can construct to I can construct this is actual tensors. The tensor, uh, I call it the simple tensor algebra of a vector space, because there is another one which is used in other places, but this is also used. Just do the tensor product k times, and you do them. So there are k, and if it's 0, you just take it to be the real numbers, and if it's 1, then you just have vector space v, and if you have 2, then you address v to cross v, etc., etc. why is this called an algebra? This is not the actual algebra. What you have to do is take the direct sum of all of them. What this means is, here you can actually define an operation. You can take a vector of this form. I will just show what is written over here. You can take a vector of this form, defining the tensor product, which is has n components, and you can another take mm, which comes from v tensor product m times, and you can take another one which comes from n times. You can define a tensor product which just squishes them together and removes the brackets or something, which will go onto a new one. But these two sets all lie in here, so it will take something like the m n. Here it will take some w m. So this will come from two different vector spaces which I am direct summing over, but there will be a new v1 vn cross w1 wm, but this is element of the same tensor algebra. So now I have defined a new vector space which is actually infinite dimensional because I'm adding over all the tensor algebras, and that will actually be a vector space, and it will also have a this operation, and that will have a tensor product operation. Tensor product actually takes two vectors and makes it a T2, and makes element of T2. So it will take V1, which is element of V, and V2, which is element of V, and it will map it to something like V1 tensor product V2. The operation is operation in T2 of V, and you can tell because the dimension of V and dimension of V1 tensor product V is like double, there cannot be a isomorphism between them, of course, and this is exclusively used in um, quantum computation, where the tensor product of two vector spaces of the two sample state spaces is a new state space of doing the whole thing together, something. Um, and there you can do not have a isomorphism between V and V cross tensor product V. This is a no cloning theorem, and maybe I'm wrong. There are more details over there, but there cannot be a linear function which does this essentially. So if you map x to x tensor product x, this cannot be linear because x1 plus x2 will map onto something which is not plus x2 tensor product x1 plus x2. Okay, so I'm proving that this function is not linear. So this will split apart. Um, x1 tensor product x2 x1 plus x1 tensor product x2 plus x2 tensor product x1 plus x2 tensor product x2, and x1 plus x2 should map to this guy plus this guy, not these two guys. So this is not actually a linear function. So at least I have heard this is the no cloning theorem. At least about more details. Now let's say, okay, simple tensor algebra. There could be another kind of tensor algebra which I will discuss later when it comes about, and there can be a symmetric algebra of a vector space. So what you do, the construction is this: take the tk of v, which is like k times tensor, k time product of vector space v, and you take the subspace which is spanned by elements of this form. I'm giving that 2 wala, k is equal to 2 wala version. Mm, it will take all these elements and like all of them, not just like the element, the subspace spanned by these elements, and it will uh, take these and to the quotient, right? Let's call that ck. It will do the quotient of that. So and what will happen here, and this will produce a new algebra. I'm not going to explain what is a quotient of a vector space or a quotient of an algebra, which I don't know anything about. But this will produce a symmetric algebra of a vector space where you have the symmetric algebra of a vector space where if you do the whole summation and you create again the same algebra, same you construct this one from the same from the case by the same procedure. Here the product will be commutative. A cross B would be same as B as a product. So the symbol must be different here. I should use as a different symbol. Let's just say I would use something like box. I don't have a good symbol for this one yet. Maybe I'll use a circle. I decided to use a circle. It will consist of a new uh, product which will be commutative. It will map to the same vector space, and I can construct another vector space which will consist of the construction is similar, but it will consist of vectors which have a I will create a vector space and which will contain vectors which will have a product that will be skew symmetric. You contain an object of this form where v1 exterior product v2 would be equal to minus v2 v1. So this will look something like a cross product, but you are not mapping v1 v2 to another v, you are mapping v1 v2 something. So you construct a new vector space to do this, and v1 intersection v2 v1 would be 0 because your map, it is the same as is negative, so it will has the twice of this has to be 0, so it has to be 0. So this is skew symmetric, and it can be used to measure. It is related to the determinant and all that. And you can do other procedures. There is a lot of details over there, but this is going to be used. Symmetric is also something I learned very recently, that it is also okay. You can embed them, but I'm not going over there. Now let's just go to the heart of the topic.